Okay, let's see the solution of test number 29. The question is, a circular wire having a radius r equal to 8 cm and resistance of r equal to 0.5 ohm is in a region with a time-varying magnetic field B out, point out of the plane as shown in the figure. If there is an induced current I equal to 0.5 milliampere in the wire, find the rate of change of the magnetic field. Okay, so we can use the Faraday's law to find the rate of change of the magnetic field. Here we want to know only the magnitude of the rate of change of the magnetic field. Okay, so we can write down the Faraday law using by consider only the magnitude of the EMF here. We know that if we write the Faraday law in the full form, it's equal to the minus of dv by dt like this. But here we want to know only the rate of change. It means that we want to know only the magnitude of the EMF, not the sign. Okay, so we put the absolute value here. The absolute value of the EMF is also equal to the absolute value of dv by dt. Here we have the B point out of the plane and the Y line on the plane, right? So it means that the surface of the area that the plane is boundary is perpendicular to the external magnetic field B out. So we can calculate the magnetic flux, right? In this case, we know that the magnetic flux is equal to BA, right? And A is the area of the circle, so it must be equal to B times pi r squared, where r is the radius of the circle. So we substitute this magnetic flux here, which is equal to B times pi r squared. Okay. And since pi and r squared are constant, it's not depend on time, we can take this term out of the derivative here. So we get pi r squared is equal times the magnitude, the absolute value of dB by dt, and this is what we want to find. On the left side, this is the EMF, and we know from Ohm's law that this EMF must equal to the product of IR, where I is the current in the wire and I is the resistance of the wire. Okay, so we can rearrange this expression to get the magnitude of dB by dt is equal to IR over pi r squared. This I is the resistance and this I is the radius. Okay, and we know all numerical value here. We have I is equal to 0.5 milliampere. Again, we need to convert this into the base unit, which is 2.5 times 10 to the minus 3 ampere. Okay, we know the resistance R in ohm, so we have not to convert anything on R, the big R here, and we have this small r is the radius is 8 centimeter, which we have to convert it to 8 times 10 to the minus 2 meter. Okay, before we substitute in our calculation. So we know our numerical value and we can put them all into this expression. And when you do that, you will find that the rate of change of the magnetic field is equal to 0.0622 Tesla per second. So the answer is 0.0622 Tesla per second, or it's equal to 62.2 millitesla per second. That is the rate of change of the magnetic field. And you can see that from this figure, the value of I point, no, the value I, the direction of I point in this direction, and this I will produce the induced magnetic field point into the plane like this, which means that this rate of change tell us that the magnetic field here will increase, right? Because the magnetic field here, the B out here increase, it means that the induced magnetic field will point into the plane to against the change of the magnetic flux in this region. That's why the induced current point in this direction. Okay, so this dB by dt show the increase of the magnetic field in this region.